Oh,
Oh,
Professor,
Professor, sorry, I had a
Yeah,
question
sure.
about the exam. So is Unit 4 exam available to take for biochem?
You can be as soon as you tell me you're ready for it.
Okay, so we just have to email you and then you'll make it available for us.
Sure. Uh-huh.
Okay, thank you.
Sure.
When
I
is the
had
last
a
time you take it?
Wait,
go ahead. Go ahead.
Oh, sorry.
Grayson?
Yeah, when was the last day we could take the exams?
I believe it's Monday.
Okay, because you said grades were due on Monday, so I wasn't sure if you like didn't want us to
I think grades are due on Tuesday.
Tuesday. Okay.
7th.
Wait, yeah, Monday's the 6th.
Yeah, grades are due on the 7th. So Monday, yeah, Monday you can have it too.
Okay, great.
Yeah.
Thank you.
I had a question about molecular structure.
Yeah.
So going back a few chapters, there's a symbol that is used to indicate partial charges for dipoles. It
Yeah.
looks like an ampersand or a G, lowercase g.
It's the
What do you?
it's the lowercase delta, the Greek letter delta.
Okay, so isn't delta a triangle? No.
Yeah, that's the uppercase, I think.
Okay, so lowercase delta is this symbol. Okay, thank you very much.
Mhm.
I had a question as well. Is this the last day that we're having class for
Well,
biochem?
I'm going to discuss that after this lecture, because tomorrow's an official holiday. But grades are not due until Tuesday, and you have all the way till Monday to take the exam. So anyway, when it's an online course, especially in a COVID-19 situation, we could have another one. We'll see. We'll talk about it.
Okay, thank you.
Professor, I actually have one question as well.
Mhm.
So you know how we have two tests?
Right.
Are those two tests our final, or is it like Unit 4 test and a Unit 5 test?
You're right in both situations. So exams 4 and 5 are 1-hour exams, right? They're just unit exams.
Right.
And finals are normally 2 hours.
Right.
And they're cumulative. But instead of making them cumulative, it's just going to be exam 4 and exam 5.
For like the unit.
Right. So that is considered the final exam. And you can take them on different days or at different times or back to back, or however you want to do it. So
All right, perfect.
Okay.
Thank you.
Sure. Okay, so any questions about what is the square of death? Okay. So then, calculating the pH of strong acids and bases in water. This is simply using stoichiometry. So a lot of students might have a problem with this. Calculate the pH of a 0.01 molar solution of hydrochloric acid. They'll tell you, oh, there's not enough information. But like what I've always tried to get you to do is write down the equation. So by the process of you writing down this equation in water, hopefully you would see that, oh, this is on your list of strong acids. It's a one-directional arrow. So when you make this solution to be 0.01, there is no HCl left. It completely goes this way. And what is it that we need to get the pH? Is simply this. So the negative log of 0.01 is 2. That's the answer. So calculate the pH of a 1 molar solution of HCl. By analogy, that's going to be 0. That's going to be 1 mole per liter, right? The log of 1 is simply 0. So yes, the pH can be 0. The strongest concentration of hydrochloric acid we can get is called fuming, or concentrated hydrochloric acid. I have some in the lab here. You open up the top and then you see eventually these fumes come up and start going down the bottle like that. That's hydrogen chloride gas coming out, mixing with water vapor and redissolving again, so you can actually see it. But it's 12 moles per liter. So the approximate, and you know, it's when you get really into far corners of concentration like this, it's approximate. The pH turns out to be -1. So yes, the pH can be negative. Because again, what is the pH? It's simply a mathematical manipulation of a number. And so here's another one that's a little bit more difficult because there's some stoichiometry involved. What about for a 0.01 moles per liter solution of magnesium hydroxide? Well, this is what it would do in water, right? Completely dissociate. And so you start out making this 0.01, but because it's so soluble, then it turns out to be 0. So the 0.1 gave you 0.01 of that and gave you 0.02 of that. So this gives us the hydroxide concentration directly. Then we can take the negative log of that and get the POH. Then there's a couple different ways we can get the pH, and then also hydronium ion concentration. So anyway, I put this in a red box. I decided not to put it on the exam. I think I might have put it on a homework. I don't quite remember. But look at this approach to this problem. Calculate the pH and all this stuff. If in a 1 molar solution, there's only 0.81 moles per liter at equilibrium. What does that mean? You made a 1 molar solution, and then when you looked at it, it wasn't 1 mole per liter of HX anymore. It was only 0.811. So what happened to that 0.189? Where'd it go? It went that way. So the stoichiometry is one of these gives me one of these. And if I make one of these, I also make one of those. And so what do we need to get the pH? Simply that. What do we need to get to Ka? Well, we have all the values here to get to Ka. So simply products over reactants, input the numbers, and there's the answer right there. So here's another way we could do problems. The pH of a 0.1 molar solution of a weak acid is 4.770. What is the Ka and the pKa? Okay, well, what do? We take the acid and we put it in water. Okay. So the pH is 4.77. So to get the hydronium ion concentration, we simply do the inverse log of that. And then now we know the concentrations of both of these, okay, right? Because of stoichiometry. And then they get the concentration of this is basically 0.1 minus whatever went to form products. So we end up getting all the numbers that we need. So there's the Ka and there's the pKa. So I just want you to see what kind of calculations are possible. Excuse me. And there's 3 methods for writing chemical reactions. We saw this in chapter 12. So there's a traditional molecular equation. So that's how we would do it for an acid-base reaction. Then there's the total ionic or complete ionic equation. So write ions only if they're soluble. Ionize strong acids and bases, since that's how they mostly exist in aqueous solution. You don't ionize weak acids and bases. So what does that mean? That's on our list of strong acids. So I'm just going to completely ionize it. That's soluble. I'm going to ionize it. That's simply what it is. And the solubility rules would tell us that this is soluble. And so then when we get the net ionic equation, we leave out the spectator ions. So I see hydrogen ion is not on this side, so it did something. Sulfate, spectator ion. Sodium, spectator ion. Hydroxide, not on this side. So when I get rid of all the spectator ions, you can see why this reaction really happens. Because you're forming water. So we don't ionize a weak acid or base. Let's see. So what does this really tell us? Strong acids, we ionize. That happens no matter whether the base is strong or weak. But if it's a weak acid, water wouldn't normally just make it ionize, so we leave it that way. But when we put a base in there, then it's going to demand that we take this hydrogen off of here and make water with it. So you see, in a way, what we're saying is that a strong acid would donate the hydrogen ion to water, even though water is a weak base. A weak acid won't, but it will give its hydrogen up to a strong base like hydroxide. So anyway, and then titrations revisited. I simply gave you a couple of more problems of titrations, but we did that in chapter 17. And then finally, with titrations, sometimes textbooks simply use this, and I don't like it. I don't like it because it says, stop trying to understand it, just memorize this equation and plug numbers in. But I did this same problem right here using their methodology, and I showed you where the equation derives from. At titration, when the titration is over, the equivalence of H plus that you added was equal to the equivalence of OH minus that you added. So those are equal. Then I work this backwards, turn that into equivalence per liter times volume. Okay. If you had to do, 100 titrations a day, yeah, you'd be using this equation. But I don't like it when we avoid having to think through a problem and we just memorize an equation. Look at the steps that we did right here. Everything we did was pre-existing things that we had learned. So you think your way through that titration problem with basic principles instead of memorizing an equation. Okay, well, I guess that's the end. This one's inappropriate, but I liked it, so I put it in there. And I'm wondering, did I put these in a different chapter? I might have, I don't know. I have to look.
I believe you did.
Did I?
Yeah,
Okay.
but it's okay. It's Chuck Norris.
Yes, it certainly is.
Professor, I have a question in that last problem you were showing there.
Mean this one?
Yeah, so one question that came up while I was doing the homework is that when you have the capital M, moles over liters, do you always have to convert, if the problem is given in milliliters, always convert that to liters, or could M also represent moles over milliliters?
Well, M is moles per liter. So you got to keep your units right, you know? You can't cancel out milliliters with liters, so that's the only point.
Okay, so always convert over to liters in these types of problems.
Yeah, well, you got to make sure your units are compatible. Otherwise, they won't cancel out.
Okay, thank you.
Mm-hmm. Okay, so let's see. Buffers is a short chapter. Covers up all my things here. Okay, so let's review all the different kind of reactions we've done with acids and bases. If you take a strong acid and a strong base, one directional arrow, that's a titration. Strong acid, weak base, weak acid, strong base, regardless. If one of them is strong, it goes to completion, and those are titration problems. But what if you have a weak acid and a weak base? Well, it doesn't go to completion. It simply goes to equilibrium. It's a reversible reaction, and those are buffer problems. So what do buffers do? They resist changes in pH. So here's water. Water has 0 buffering capacity. So if I simply take an acid and I put it in water, I directly change the pH. Same with hydroxide, I directly change the pH. But a buffered solution will contain buffers, which is a combination of a weak acid and a weak base. So look what happens if I put hydroxide in here. Instead of it affecting the pH directly, it's going to react with this weak acid and convert some of that weak acid into its conjugate, its conjugate base. So instead of just showing up directly, it's going to be absorbed, at least in part, by this weak acid. Similar with if I add acid to it, it's going to react with the weak base and convert some of it into the weak acid, its conjugate acid. So a good buffer will have significant amounts of both the weak base and the weak acid. The greatest buffering capacity is what the term we use, is when they're equal. Okay, so which would make a good buffer pair? Strong acid? No. This might be a weak acid, that would be a weak base. Yes, that would work. No, this wouldn't work because simply you would make water, right? Strong acid? Nope. That's not SO4, that's SO3, not on your list. So that's a weak acid, a weak base, so that would work. So how do we calculate the pH of a buffered solution? And this is the only problem I'm going to teach you how to do for this chapter. Because if you really look at it, all the standardized exams that you might have to take, this is the kind of problem that they're going to ask. So we'll just do these kind of problems, be able to calculate the pH of a buffered solution. So what do? We base everything on the acid. See, that's a chemistry joke. Sorry. So we already know how to take the acid and write its equation for dissolving in water, right? We already know how to get the equilibrium constant for that, products over reactants. So notice, here's the weak base, here's the weak acid, right? And so what do they ask for again? The pH. So all we have to do is solve algebraically for this, right? And then input the numbers. That's all. So you input the numbers, you get that, then take the negative log of it. Some problems might not give you the Ka, they might give you the pKa. So you have to remember how to get back and forth between Ka and pKa. So now if I'm looking at this equilibrium expression right here, I got 1, 2, 3, 4 things. You got one equation. You can only solve for one unknown. So like I said, I'm not going to have you solve for this or for this or for this, simply for this. Okay, because we're just going to get the pH of these problems. So let's just do one. Calculate the pH of a buffer made by adding sodium bicarbonate and sodium carbonate. So at equilibrium, here are the concentrations, and then here's the Ka. So now I have to decide which one is the acid and which one is the base. This doesn't have any hydrogens. It cannot be the acid. So this has to be the acid. So the acid is hydrogen carbonate. Sodium is just the counter ion, right? So I take the acid, I put it in water, get the products over reactants, and then mathematically I'm simply solving for hydronium ion concentration, and then I just input the numbers. That's it. Take the negative log. Notice in blue, I put the buffering capacity, right? Simply the ratio of weak acid to weak base. Here, because these are the same concentration, this is maximum buffering capacity. So this solution is going to be a very, very good buffer at pH 10.25. If I change the pH, it probably won't be a good buffer because I'll change the ratio of weak acid to weak base. Also notice that when these are equal, they cancel out. What does that mean? So they cancel out, the pH, not the pH, the hydronium ion concentration is really equal to the equilibrium constant. And then the pH is really equal to the pKa. Well, why is that important? Because a chemist can go look at a list of weak acids and say, I want to get a good buffering system at pH 7. So what do? I choose a weak acid with a pKa close to pH 7. Say the pKa was exactly 7. If I took a 50-50 mixture of the acid and its conjugate base, put it in solution, the pH would be 7. So to summarize, this is what we use for buffering capacity. This obviously gives us the pH, and the number, a large number means that you get mostly products, a small number means you get mostly reactants. And then for a weak diprotic acid, notice that I'm taking only one hydrogen off. So here's the acid, here's the base. When I take this and go to the other side again, that's the acid, that's the base. So because it's on the product side, those are conjugate acid and conjugate base. So notice that the conjugate base of H2A is HA minus, right? So then I started throwing the numbers around a little bit. So here I have a 1-to-1 ratio. The pH was 10.25. What if I change that ratio a little bit? Look, now I have twice as much of the conjugate base as I do of the acid. And what happened to the pH? Oh, it's 10.55 instead of 10.25. Okay, it changed, but not very much. And how would I have accomplished this? I have this at equilibrium, right? What did I do to make this go up? I added some other base, didn't I? So I made it so this is twice the concentration as this, and still the pH didn't change that much. Then I made it the other way, so the pH changes, but not that much. And then I did it crazy. Now there's 1,000 times more hydrogen carbonate than there is carbonate. And did the pH change dramatically? Yes, it did. Because now you don't have good buffering capacity. So here's another one that's just very, very similar. The only thing that's different here is that instead of giving you the Ka, I gave you the pKa. So you would have to convert the pKa into the Ka, and then you do the same thing. So calculate the pH of a buffer made by adding so much sodium dihydrogen phosphate and so much sodium hydrogen phosphate. Here's the pKa. Which one is the acid? That has 2 hydrogens, that has only 1. That's the acid. So I base everything on the acid. Here's the acid dissolving in water. Here's the equilibrium constant, sulfur, hydronium ion. Just substitute all my numbers and there's the answer. Take the negative log of that and there's your pH. So, using this as an example, what happens to the pH when you add 0.01 moles of HCl to 1 liter of acid? Strong acid completely ionizes, right? Notice that the pH is 2. You already know how to do this calculation. But now, what would happen if you add 0.01 moles of HCl to 1 liter of the above buffer, this one right here, at pH 7.5? Okay, so again, the HCl completely ionizes. So you got 0.01 moles hydrogen ion that you added. But what do we do? Notice that if I'm adding acid, the acid is going to increase by 0.01. What's going to happen to the base? It's going to decrease by 0.01. So now I have new numbers to put in here. And notice that I simply do the calculations. I get pH 7.4. So if I were to put this amount of acid into water, the pH is 2. If I put that same amount of acid into this buffered solution that was at 7.5, it now simply drops to 7.4 something. So not that it doesn't change, but it resists changes to it. It buffers it. So here's the way I was taught this, and I was taught bad. What they do is say, oh, you memorize the Henderson-Hasselbalch equation. And I remember having them memorize this, and I basically argued with my professor about it, because my professor for chemistry was my my high school friend's father. Anyway, I'm going to show you where it's derived from. Here is that expression, right? That's exactly what we were solving up here. That's all it is, right? So then I take this equation and I turn it upside down. Just flip the whole thing over. And what do I have? This right here is now the definition of pH. This right here is the definition of pKa. And this right here simply is what it is. But tell me, memorizing this takes you away from all this process that we did right here. But all these process was simply stuff that we've learned before. So we're just reinforcing that knowledge. It's all stuff that you know how to do before. So again, I don't teach it that way. Then we have 3 major blood buffers. Your blood is extremely well buffered. It has to be. If your pH goes out of whack for either one way or the other, you start passing out. Respiratory alkalosis, acidosis, you'll pass out. So what are the 3 major blood buffers? I put carbonic acid. Textbooks always refer to this as bicarbonate, but they're essentially wrong because carbonic acid has a pKa of 6.37. Bicarbonate is 10.3. Well, wait a minute. We're trying to get to 7 point something, right? 7.35 about. So this is way closer. So I take the weak acid, put it in water, okay? We talk about products over reactants, but what's really important, what they talk about all the time, is the ratio from one to another. So in a real person, it's about 25 millimoles to 2.5, so it's about a 10-to-1 ratio. Okay, make sense? And where does that come from? Where does carbonic acid come from? Here's glucose. You breathe in oxygen, you oxidize glucose to CO2 in water. CO2 formed in water is forced to go through this chemical reaction to form carbonic acid, which is what we have up there. And that's where we get this ratio right here. So you'll see in a little bit that your breathing rate is what controls this ratio right here, and therefore it controls the pH of your blood. Another important one is dihydrogen phosphate, because the pKa is almost what the pH of blood is normally. Certainly not going to be a hydrogen phosphate, that's way too far away. So again, I take the weak acid, put it in water. What we really think about is the ratio between the weak base and the weak acid. In this case is about 1.6 to 1. So dihydrogen phosphate is a very important buffer, and you cannot change it. It's simply fixed. It's one of your electrolytes. Another reason why your electrolyte concentration is extremely important, because if you don't have electrolyte balance, you're not going to be able to maintain your blood pH properly. The third one are proteins. So proteins are a little bit hard to explain because you haven't had a bunch of other stuff possibly. But here's what a protein looks like. It's made up of amino acids. Here's a typical amino acid. So here's the amino group. Here's the acid group. This is in this protonated form. The pKa for the amino group is about 9 something. The pKa for the carboxylic acid group is about 4 something. What we often do is simply take the mathematical averages of the 2 or more pKa. So in this case, it would be 6.75. So proteins have amino groups and carboxylic acid groups sticking out of them. And so we're talking about pKa average of about 6.75, which is, half a pH unit away from what normal would be. If you look at the ratio, it's a little bit greater than 1 to 1. So this has really, really good buffering capacity. That means that proteins are exceptionally important buffers. Not only that, your blood is so thick with protein, it's about 72 milligrams per mil. That's crazy. The most concentrated protein drink you can make from commercial bodybuilding powders is about, that much. Depends on what you're reading. Because you guys believe everything you hear about bodybuilding powders, right? Yeah. So going back to blood and vampires, if you were a vampire, whose blood would you most likely want to drink? Not that skinny drug addict downtown. You want some bodybuilder who's spending all his money on pumping protein and vitamins into his blood. Yeah. So your blood pH is monitored by the central nervous system that controls your breathing rate. So a lower pH in higher hydrogen ion concentration causes an increase in breathing rate because you're trying to get rid of carbon dioxide. So here's the series of equilibrium. Okay. So what happens if you hold your breath? If you hold your breath, you're producing CO2 faster than you're getting rid of it. So this concentration goes up. That's the stress. Okay. If you add something as a reactant, wouldn't you expect to get more product? So notice how I put this together. The stress on the bottom, the result is on the top. That's just my thing to try to organize stuff. What I really need to do is figure out which direction this arrow is going to go. If I add more reactant, I expect to get more product. Now I'm adding more of this, I expect to get more product. And what happens to the hydrogen ion? That goes up, so the pH goes down. So if you hold your breath long enough, you eventually pass out due to what's called respiratory acidosis. And then your autonomic nervous system takes over and says, hey, stupid, you forgot to breathe, so we're going to do it for you. And unfortunately, if you're underwater when that happens, you breathe in water and then you drown. What happens if you hyperventilate? You could pass out due to respiratory alkalosis. What does that mean? If you hyperventilate, you're removing CO2 from your body faster than you're forming it. So the reaction goes that way to try to replace it. Okay. So once I figure out which way the arrow goes, then I can see, well, it's moving this way, that's going to go down. So this is going down, it's going to move this way, that's going to go down. So what happens here? Hydrogen ion concentration goes down. What does that do to the pH? It makes it more alkaline, higher pH. And so I know people who've drowned from like free diving and stuff like that. and they're experienced free divers. I'm worried about it now because my son is into it, and now my grandson wants to get into it. I don't know. He has friends that are really, really, you know, heavy duty free divers, but it scares me because a lot of people die from shallow water blackout. They hyperventilate before they dive down, believing that they're getting rid of more CO2 so they can stay underwater that much longer, and they pass out. And then their autonomic nervous system makes them breathe underwater, and then you drown. So other organs in your body work to moderate your body's pH. So here's your lungs, the most important, but you have other systems like, you know, proteins and dihydrogen phosphate, and the kidneys. The kidneys make urine that can either be acidic or basic. And yeah, so it all works together. So if you were to eat a bunch of really acidic food, does that mean that your body's pH becomes acidic? The answer is no. You will breathe faster for a period of time. Your buffering system will help you out, and your kidneys will excrete more acidic urine. So here's some combinations just to show you a couple of different things to give you a perspective. Strong acid, strong base, 100% ionization, right? Strong acid and water, 100% ionization. That would be about approaching 0, so you get a really, really large equilibrium constant. Weak acid and strong base goes all the way. It's a titration problem. So even though the weak acid might give you a small equilibrium constant, same thing for weak acid and strong base, you get a small equilibrium constant. Yeah. You know, some things, when you dissolve it into water, it will have acid-base properties, even though you might not even be thinking of it. Like, say, sodium sulfite, what would that do? Would that change the pH? Yes, it would. A little bit. And then if you take another chemistry course, these things might be of use, because these are kind of off-the-wall things that people don't necessarily quite understand. So the concentration of water, we were able to calculate that, right? This from its approximate density. The definition of Ka derives from this relationship, putting an acid into water, right? And then products over reactants. Same thing for Kb, right? Put a base into water, and then it's products over reactants. And now, what if we multiply Ka times Kb? Okay, so look, we did that. Look at all these things that cancel out now. Ka times Kb is equal to this, which is simply Kw, which we know the value of. So in other words, Ka times Kb is equal to Kw, which is 10 to the minus 14th. So not in our course, but in another course, you might be able to use this, right? If they give you the Ka, what's the Kb? Well, there's the relationship. Now, if I take this relationship right here, and I inverse it and take the logarithm of it, what do I get? pKa plus pKb is equal to 14. So we don't need to use these in this course, but another course that could be very useful for you. And for water, you'll look it up and you'll see that the pKa is 15.7. And I remember this happened to me and I'm like, what the heck? The pKa should be 14. But here's what they do, and they don't bother to tell you this. Almost every time you look up the pKa for water, it's 15.7 because they were using heterogeneous equilibrium and they left in the concentration of water. That's how they got that. If you do it in a homogeneous equilibrium, you leave out the concentration of water and you get pKa of 14. So these books are so irritating. They do all these problems with homogeneous equilibrium, then they tell you the pKa for water in heterogeneous equilibrium. I don't get it. Okay, so here's some of my favorite cartoons. So this always reminds me of my youngest son. My youngest son went to Asset School, the most expensive school in the state of Hawaii, but I couldn't put him in any other school because he was too out there. But yeah, they were nerds over there.
Wait, Asset's high school?
I'm sorry?
Asset's high school?
Asset School.
Oh, where is that?
It's out by the airport.
Oh, okay, never mind. All right, never mind.
Yeah. And then here's the I in team. Yeah. Anyway. Okay, so any questions on this very short chapter? So what is it that you need to know how to do for this chapter? Okay, you know what a strong acid and a weak acid is, know what a good buffer would be, right? Weak acid and a weak base. And then calculate the pH of a buffer. And that's it. And you should know a little bit about your own blood, don't you think? So let's see. It's so awkward. Everything covers everything up. Okay, so here's the last chapter. It's also pretty short. And I don't put a lot of stuff on the exam from this chapter. But what we do is we look in much more detail into Le Chatelier's principle, which we were just using. So we identify the stress. We use that to decide which direction the arrow will go. And then we look at what's going to happen. So let's see. What happens to the ammonia concentration when the nitrogen concentration is increased? So the system is at equilibrium. It didn't go to completion. All the concentrations are just stagnant. And then the stress is that somebody came along and increased the concentration of N2. Well, you added more reactant. So you're going to push the reaction this way. If you push up here, you push it that way. So everything over here is going to go up. And why is this going to go down? It's stoichiometry. Every time one of these goes that way, it takes 3 of these with it. You see how that works? Here's another way to look at Le Chatelier's principle. So here's the equilibrium constant for this reaction. And we said it was a constant, right? Hopefully you believe me. Well, look what happens. The stress is I added more nitrogen. That's the stress. Now, mathematically, how could I counteract that stress and keep the constant the same? Well, if this goes up, that could go up. Oh, it does. Or if that increases, you could counteract by that decreasing, which it does. So it makes perfect sense. What would happen to the ammonia concentration if the nitrogen was decreased? So now the stress is that you're removing this. It's going to move that way to try to replace it. Now, is the chemical reaction thinking about what it's going to do? No. What's going on here is simply the rate. If I take this away, the concentration is lower, so the rate in going that direction is going to be lower, but the rate in this direction is still going to be fast, so the whole thing moves this way. So, what about if the temperature was decreased? Well, guess what? We treat the temperature just like any other entity in the reaction. If we decrease the temperature, it's going to try to move that way to try to replace it. Once I get the arrow direction, I can see everything else is going to just fall in place. Everything over here is going to go up. Everything here is going to go down. And this one's a little bit more difficult. What happens to the ammonia if the pressure is increased? So we did the chapter on gases. So here I solve PV equals nRT for pressure, right? What if all these were kept constant? Then the pressure is going to be proportional to the number of moles. Okay, so that means if I reduce the number of moles of gas, wouldn't you expect the pressure to go down? Well, here I have 4 gas particles. Here I have only 2. Does that make sense? So if I increase the pressure and wants to counteract that, here's more gas particles, here's less. It's going to go towards having less gas particles to get the pressure back to normal again. So everything here goes up, everything here goes down. So here's what's essentially the Haber process. And it was the production of huge amounts of ammonia. This was tremendously important because about the age right after World War II, they expected there to be a huge famine. Populations were going back up after the war, and how are we going to feed all these people? Well, in part, it was the Haber process that saved humanity from a huge starvation event, because ammonia is used to make so many fertilizers. So companies were maximizing the production of ammonia. So the more ammonia you make, the more money you're going to make. So you want the reaction to go that way. That's what you want. So how would you make this arrow go that way? What would you do to the pressures of these gases? You increase them, right? You do this under higher pressure. But look what happens. As you go this way, what does the temperature start to do? It goes up. That's going to counter what you're trying to do. So what would you do to the temperature? You cool it down. You remove heat to make this reaction come this way. And then your goal is to produce ammonia. But why do I have this arrow over here? Because if I were to remove the ammonia as it's being formed, I would make this even come faster. So here's the idea. I set up the technology so that I have higher pressures in here, and I check the temperature so that I will get ammonia to precipitate and form a liquid. Now I've removed ammonia from where the reaction takes place. It's turned into a liquid. We've seen that several times, right? I can drain that off into another container, maintain the pressure and temperature, and keep it as a liquid. Now it's not at equilibrium. This thing cannot even get close to equilibrium. It's racing towards equilibrium, but never getting there. Because every time we form ammonia, it's removed as liquid. Now, why do I think I could get the liquid to liquefy and not the nitrogen and the hydrogen? Difference electronegativity, 0. Same thing here, 0. What do we know about ammonia? Polar molecule, behaves like a little magnet. So I will find a temperature. Well, this will precipitate as a liquid, and the others will remain as gases. So let's look at the equilibrium constants. We know how to do that. So here's when ammonia is a gas, it's like all the other gases. Here is when ammonia is a liquid. You see the difference? We changed the equilibrium constant. We manipulated this chemical reaction to make it do what we wanted, and we changed the equilibrium constant. Now here's a little bit of introduction to rates. So if I look at this reaction, which is too far up there, okay, well, I can do it. These 4 things right here have to collide with one another to go that direction. 3 are the same, 1 is this different, right? But 4 things have to collide with one another to be able to get in that, to go in that direction. So what I'm telling you is that the rate in the forward direction is equal to some constant times the concentration of each of those 4 things that have to collide with one another. If I double the concentration of this, I approximately double the rate because they collide more often. And all I did was combine like terms, right? So that's raised to the 3rd power, that's to the 1st power. What about if ammonia is a liquid? Well, nothing changes, right? So in both cases, the rate going in the forward direction is the same. What about the reverse direction? 2 of these have to collide with one another to go in that direction. Okay, so in the regular reaction, I combine the like terms, right? So the rate in the reverse direction will be depending upon the concentration of the ammonia. But what would happen if I don't have any ammonia up here? It's all been taken down into liquid phase. Well then, if you look at it in this thing, this is approaching 0, but there is no rate because that is 0. So we've effectively stopped the reverse rate from happening. So now it's racing towards equilibrium. It can never get there. Now if I add a catalyst, I'll make it go even faster. And this is a very interesting concept. I don't know how many chemistry courses it took me to finally understand it. But here's the energy diagram, which we've seen a couple of times before. So here's the reactants, here's the products. That's the amount of energy that they have, right? Potential energy. So this difference right here determines the equilibrium constant. So what determines the rate? It's the magnitude of this energy barrier that it has to go over. That's what determines the rate. It's called the activation energy. What does a catalyst do? It simply lowers the activation energy. So the rate goes faster. But notice, if I lower this barrier right here, I make the reverse rate faster and the forward rate faster. So if I have a chemical reaction that's already at equilibrium, and I put a catalyst in there, is it going to change the equilibrium? The answer is no. The catalyst just helps you get the equilibrium faster. The equilibrium itself is determined by this other factor over here. So here's a couple more. Here's one type of glasses that get darker in the sun. It's all equilibrium. The energy is in the form of light. That's this energy. And remember how we treat energy just like any other entity, like how we did it here. And then this next part over here, it's really just conceptual. So this is a simple reaction. Notice that it's an endothermic reaction. I have to put energy into my reactants to get them up to the energy of the products. But it's good because these are the same. So here are the reactants. Here are the products. Look at the energy. The highest energy state is right here at the transition state. What do we mean by the transition state? Well, you're transitioning between the reactants and the products. But part of the explanation that needs to be added is this. What the heck is the transition state? They have to bang into each other in the right direction, in the right strength. But what you're trying to do in the transition state is these bonds right here are halfway broken, and these bonds right here are halfway formed. You're not meeting the octet rule and the duet rule right there. That's why this is the highest energy state. So going back to what the catalyst does, what does it do right there? It changes the transition state. That's what it does. So, let's see. How does a catalyst work? Okay, well, it does a couple of things. It concentrates the reactants on the catalyst, bringing the reactants into closer proximity. And I'm using words that are right out of every single biochemistry textbook. And it puts them into the right orientation. It puts strain on the bonds. And I have to add this one. This supplies chemical groups. Okay. So I'm going to talk about enzymes here for a minute because I think they're the most complex of catalysts. Simple catalysts, they just supply electrons or hydrogen ions or something like that. Enzymes are more complex. But what do I mean by supplying chemical groups? Here's a protein. You see the pH out here might be in your blood, right? About 7.35. If I put a bunch of functional groups here, like amino acids that have acidic functional groups on there, the effective pH on the surface of this protein in here can be way different than out here. So if I had a chemical reaction that would normally be speeded up by, say, acidic conditions, I would guarantee you that you go to nature, find the enzyme that does that same chemical reaction, and it's going to have a bunch of acidic functional groups in the active site of the enzyme. So this enzyme was produced after millions of years of evolution to be the best it can at what it does. And what do I mean by evolution? Well, whatever the chemical reaction is, if I have a mutation that makes my enzyme work more efficiently, that gives me a little bit better possibility for survival, at least to the age of reproduction. So my genes are more likely to get down to the next generation than someone who has the lesser mutation, for example. Okay. So here's an example. I used methyltransferase. What a methyltransferase does is it takes a methyl group from one reactant and puts it onto another reactant. Okay, so here's reactant A with the methyl group. Here's reactant B without the methyl group. So essentially it takes the methyl group and puts it on the other reactant. That's what it does. So how does it do that? Well, the enzyme gets involved with the transition state. The enzyme changes how the transition state is occurring. And it breaks it up into smaller, easier to do steps. So folic acid is something you need in your diet, right? It's really a vitamin. So most of the vitamins work with enzymes as cofactors. So the protein itself doesn't have the chemistry to do this, but the folic acid provides that little extra chemistry. So it interacts with reactant A that has the methyl group and says, you know what, give me that methyl group for a minute, and it holds on to it. Okay, see, it's holding on to it. So now this empty one might go away, and then the new one come in, and then it says, hey, I got this methyl group for you, and it puts it right on there. And there's lots of other things that we could talk about, and this is a whole chapter in Biochem 341 that we'll talk about how an enzyme performs all these functions. I find it absolutely fascinating that there is nothing about an enzyme that doesn't obey the laws of chemistry and physics. But they do basically magical stuff. This is the reason why we're alive. Essentially, I don't really. Here's something I could play with. Okay. I know it's kind of lame, but whatever. So say I'm the enzyme, okay, and this is the methyl group. This binds to me. I take off and I hold on to the methyl group for a minute. Then this thing bangs into me over here. But by design of my body, it's forced into this correct orientation for this to go right, not compatible, right on there. So if you left it up to just fate bouncing around in a test tube, then these things got to have all kinds of different collisions that are not going to work. And so that's the reason why an enzyme can speed up a chemical reaction easily by 1 billion-fold. Now say this was a folic acid dependent enzyme and you didn't have enough folic acid in your diet. That means that if that's this enzyme right here, that enzyme it's not going to be working very effectively. If that enzyme is meant to take B and turn it into C, there could be consequences down the line because it's part of a metabolic pathway. If you can't make C, you're not going to make D. You're not going to make any of these other ones. So that would be a metabolic disease, but that metabolic disease could be fixed by providing that micronutrient. If it's this part of the enzyme that was defective, well, then you have a metabolic disease, but it's a genetic disease. The gene coding for that protein is defective, but you will still have the same consequences in metabolic pathways. So now, reaction rates, we could go into this into some little bit more detail. Say I take this very simple reaction right here. The rate in the forward direction is going to be equal to some rate constant, which are always lowercase k's, right? Times the concentration of A times the concentration of B. So if this were the case, what would the rate do if I doubled the concentration of A? Well, then the rate would double. If I doubled the concentration of A and B, then the rate would quadruple, right? So here's a real situation. The rate in the forward direction is going to be equal to 2 of these hydrogen peroxide molecules banging into each other. So now I have this situation. Where do I get rate constants from? Well, I measure the concentration and I measure the rate. So here's the relationship. The rate constant is simply mathematically the rate divided by the concentration. Here's where I find students are, no matter what courses they've taken, they don't know what a rate is for some reason. So using that same reaction, I can get it up here, okay? We start off with a container with just the reactants in it. We start the reaction, then as time goes on, you get some products for me and you have some reactant left over. So here's time, here's the concentration of one of the products. There is a point, a section of this curve right here before it starts to wane off like this. And the reason why this is going to taper off is because you're running out of hydrogen peroxide here. But you take this linear part right here, and that gives you the rate. Okay? That's how we get the rate. So what kind of things affect the rate? Well, if you increase the reactant concentrations, you get more collisions, you increase the rate. If you increase the temperature, you're getting more collisions, and the collisions are going to be harder. Or if you put a catalyst in there, then you will affect the rate. So here's a scenario of the enzyme catalase, which you have in your body to break down hydrogen peroxide when it forms. You break it down safely into water and into oxygen. Probably the original catalase just happened to be a protein that picked up an iron atom from the environment, and that really helped that particular aerobic organism to survive. So if this is hydrogen peroxide and this is catalase, then this you can see is going to get sucked right into there. The enzyme was designed to fit the substrate or the reactant perfectly. They're designed to be attracted to each other. So when that gets sucked in there, even if it hits over here, it gets sucked in over here. What is right there in the place where we need to break that bond? It's the iron atom. What does the iron atom do? Takes some electrons, gives some electrons. You end up making it much easier to break that bond. Okay. So here's two definitions of equilibrium. One, the concentration is no longer changed with time. Two, the rates become equal. So look, here we have H2 in this case, a reactant, very, very high concentration. As the reaction starts, it goes down, keeps going down, and gets to some point where it stays the same. That's because it's at equilibrium. Here's one of the products. It's 0 in the beginning, then it increases with time, and then it gets to the point where, it stays the same at equilibrium. Notice that neither one of these is 0. Let's look at the rate in the forward direction. In the beginning, you have a whole bunch of reactant, so the rate's going to be fast. But as you start to start to change the reactant into product, the concentration goes down, so the rate goes down. Then it goes down to some point and just stays there. Reverse direction in the beginning is 0 because there is no product for it to work on. But as the reaction proceeds, you start to get some product formed so they can break it back down into reactants again. So the rate goes up. Notice that the rates become equal and the rate is not 0. So if you look at a chemical reaction and the reactants and product concentrations aren't changing anymore, you can say, oh, it's at equilibrium. That means nothing's happening? No. What's happening is the rate in reverse and the rate in the forward are the same rate. Again, that's equilibrium. You got 20 people in a room, and every 5 minutes, one person goes out and another person comes in. You still got 20 people in the room. But it's not static, it's dynamic. And so here's another definition of the equilibrium constant, why we call it a constant. I took that same reaction. So here's the rate in the forward direction. Here's the rate in the reverse direction at equilibrium. So then I took all the constants and put them on one side and all the all the variables on the other side. And so, look, this is the definition of products over reactants, right? If I take a constant and divide by another constant, what kind of a number do I get? A constant. So we won't do this, but I gave you the example. It could be done. It's just applying stoichiometry to chemical reactions. And finally, and this is not really, I don't even remember if it's on the exam or not. I have to look, but see this reaction? This equation right here? G is simply usable energy. H is energy that comes from breaking and forming bonds. S is energy coming from entropy. Entropy is a state of randomness. Notice that it's multiplied by temperature, because if I increase temperature, I increase randomness. So here's some situations where you have an increase in randomness. When a solid turns into a liquid turns into a gas, and all that's caused by adding heat energy, right? When you form more molecules from fewer molecules, and when the volume is increased. Here's the burning of gasoline. Octane is a minor component of gasoline, but I used it anyway. So here's the G, that's just the potential energy for the reactants. Here it is for the products. Notice that that difference in G right here is simply the mathematical difference right here. And what does it mean if that's a negative number? That means that they took this and subtracted this. But you see, it's written on this side. That means that you have more energy in the reactants than you do in the products, so you will give off that heat energy. Here's the transition state, right? So that's how it's all put together. Now, if you take that gasoline and put it in a bucket and throw a match on it, you can measure the delta H, you can measure the temperature change, but you cannot harvest energy from the change in entropy. What is the change in entropy? Okay, you're going from a liquid to gases. Here's 27 molecules. Here's more than that, 34 molecules, but you give off heat to expand these gases. So those gases may be expanding, but there's no machine to take advantage of it. You can't harvest it. So the internal combustion engine takes advantage of that change in volume, doesn't it? And the biological machines are proteins. Okay. So here's an example of energy from ATP being used to do mechanical work, harvesting that energy to do work. So your muscles are like this, and when ATP is hydrolyzed, they shorten like this. We have what's called the conformational change, where these two thick and thin filaments interact. That conformational change occurs on the protein. You're making the protein move, and that movement of the protein is making another protein move. That's work. Here's another example. Using ATP to do work of moving ions across a membrane. You create an electrochemical gradient in this particular case. Okay. So what causes that to happen? You see the protein this way, now the protein is that way. That's a conformational change. Here's what a conformational change is. If I move any of these things like this, rotation about single bonds is allowable. That's what we mean by a conformational change. And anyway, that's the end. I don't know, I just had to figure out something to do with that picture of the Chihuahua. Of course, you made it to the end, and you should be looking for your pot of gold now, right? So sorry about all the bad jokes and everything this summer session. It's not my fault. God made me do it. I
enjoyed them all at the end.
That's good. least somebody does. So does anybody have any questions about this chapter? Any chapter? Let's see. So tomorrow is supposed to be a holiday. I know I'll probably end up working anyway. I guess theoretically you're supposed to have your final exam today, but I've never done it that way. I've always given people the option. So you do need to be done by Monday at 9 p.m. Okay. I have to turn grades in the next day. So notice I've been trying to look through Laulima. When people turn in the homework, I email them the answer key. So you have the answer keys right away. And yeah. So you can take exam 4 on a different day than exam 5. I'm just thinking, am I going to be close to a computer all day long? I'm not sure, but we'll figure that out. So any questions about anything?
If you want to do a test, we can do it on like Saturday or Sunday and just or email you in the morning.
Yeah, sure.
Okay.
So there is a possibility that I might go surfing one morning or something and not be available to do that for a couple hours. But yeah, I'll figure out some way.
Yeah. Hello, Professor. I didn't see the homework of Unit 4 and the Unit 5.
Are you in Chemistry 100?
Yeah.
Yeah, so you haven't gotten there yet.
Oh.
Yeah.
Oh, okay. So all this.
Oh yeah,
course
you're
is
the one who's done everything so far, and it's just waiting for the exam. Yeah. Yeah. We're not used to having students like you.
Okay. Okay. Okay.
But I can upload the homework for you if you want to get started on the next unit.
That would be fine. Thank you.
Okay, sure thing.
Thank you.
For Chem 100, what's going to happen next? Are we meeting on Monday or?
Well, I'm waiting to get information from my new class that starts on Monday.
Okay.
Yeah, but I'll let you know.
Okay. Are we going to be taking the class together with your new class?
Oh no, because it's totally a different animal.
Oh, okay. Okay.
Yeah, totally different animal.
All right. So we'll just sit tight for your email then.
Yeah. Yeah.
Okay.
Fine. I have no idea what's happening because I don't normally do this online, right? So it was the COVID-19 thing that made us do it. Okay, well, if you have any other questions, just feel free to email, and have a great day and 4th of July. And I don't know what your plans are for 4th of July. I'm not even sure what I'm going to do. It's not your normal 4th of July, is it?
Not the same.
Yeah.
Professor,
I'm sorry, go ahead.
sorry, would we be able to have a review session tomorrow, or would you be busy?
Well, I thought about it, but I never really came to a conclusion. But yeah, let me just email you about that. Okay.
Thank you.
Mm-hmm. So by the way, University of California system had previously said that their fall semester was going to be open again, right? Like regular face-to-face. And they just retracted that. Apparently it's going to be all online now.
Wow.
So, yeah, we'll see what happens.
Yeah, all the restaurants were opened and they all closed back down today.
Is that right?
You can't do any more dine-in before they were allowing it.
Yeah. Unbelievable, huh?
What a time to be alive,
Yeah.
honestly.
So many variables we don't know about too about this virus. So it's an RNA virus, so it mutates quite often, just like influenza, flu. We don't know if you have antibodies to this version, will be still work against it if you get exposed to a slightly different version.
Right.
My friend, who's a Japanese national, is in the banking business in Hawaii, but does, American versus and Japanese. She said that they believe the virus in Japan is a much virulent strain. And when they start opening up tourism, our tourists come from all over the place. So, yeah, we'll see what happens. Scary.
Yep.
On that happy note, okay, so email if you have any questions, okay?
Okay.
And you guys take care.
Have a happy 4th.
Thank you.
You
Thank
do the
you.
same. Take care now. Bye.
Appreciate it.